Hello everyone, my name is Jawad Tahir, and today I will be presenting you my doctoral research proposal, which is titled Config 2.0 towards reinforcement learning based configuration of stream processing system. Let's start our talk by building some motivation behind the research proposal topic. As the amount of the data available to process is increasing by the second, one single machine cannot scale with the amount of data available. Hence, the industry is moving towards distributed processing system, where we pool the resources of multiple nodes to process the huge amount of data. Crashes and failure are quite common in any IT infrastructure. For example, Beidou reported to have more than 290,000 hardware faults in the cluster in 4 years. These crashes and failure cause suboptimal performance in any distributed system. For example, here we can see the drop in the throughput of a system due to a node crash. As these crashes and failures are quite common in any infrastructure, these distributed stream processing systems employ different fault recovery mechanisms. For example, they can store the state of the whole system on a state backend, and in case of a failure, they can reinstate the state from state backend and then replay those events to recover from a fault. Now, the problem that we face here is that there is a trade-off between the frequency of a snapshot and the cost of the snapshot. More frequent snapshot will result in faster recovery from the failure, but will also incur higher cost. The performance of recovery also depends on the performance of the state backend store from where it is reading and writing the system's state, for example, RocksDB or Apache Redis. But the performance tuning of the system is an arduous task because of large number of tuning parameters, or a configuration may produce undesirable results under different workload. Here I will show you an excerpt from GitHub page of RocksDB, where even the developers of RocksDB claim to not fully understand the effect of each configuration change, and they recommended to experiment and benchmark different configurations. Now let's see how can we solve our optimal configuration search problem. One possible solution could be using reinforcement learning to find the optimal configuration of a distributed stream processing system. Now let's see what reinforcement learning is and why it is beneficial in our case. Reinforcement learning system consists of an object in an environment, and the object is at some state S. The agent then performs some action A that will change the state of object from S to S prime. That state change is then observed by the agent. The agent then calculates a reward function based on its new altered state S prime, and based on this reward function, update its policy. The agent then performs these four operations iteratively and then learn a policy which maximizes the reward, which in our case would be the optimal recovery performance of a DSPS. And the reason we chose reinforcement learning is that it does not require a huge amount of label data as compared to other machine learning techniques, for example, neural networks, where one needs huge amount of label data to train the neural network. Now let's see what are the research questions that this doctoral study aims to answer. This doctoral study consists of two goals. The first goal is to investigate the impacts of various failures on the performance of different distributed stream processing systems. And the questions that we will be trying to answer in this goal would be which failures degrades the performance and to what extent? How did this system recover under different configurations? Or which system can better handle a specific type of a failure, or how do processing guarantees like at least once and exactly a once affect the performance of the recovery. And the second goal of this doctoral study is to develop a reinforcement learning based agent which configures a distributed stream processing system to minimize the impact of failures on the performance. And the questions that we will try to answer during this goal would be how to model a distributed stream processing systems environment, or can the dimensionality of a system's environment can be reduced, or what factors should be part of the reward function, or what is the baseline performance. Now I will explain the approach that we are taking to reach our research goals. For the first research goal, we will start processing the stream of events that we are getting on a specific distributed stream processing system. And in that system, we will inject some failures. And then we will see the impact of this failure on the performance of the system. For the second research goal, we can model those four steps in a reinforcement learning environment as follows. First, we will apply different configuration on a DSPS, and then we will observe the performance of this DSPS with this configuration under fault. These measurements will be used to calculate the reward function, which then will drive the policy of the system. This way, we can come up with a reinforcement learning agent which can automatically configure a DSPS to maximize the performance. Now, let's see the current status of the research that we are conducting. We have shortlisted four distributed stream processing systems to run our benchmark on, which are Apache Kafka Stream, Apache Storm, Apache Flink, and Apache Spark. And our pipeline consists of different stateful and stateless operations, and the data is ingested through a multi-broker Kafka cluster. We will also run our benchmark on different processing guarantees, like exactly once and at least once, and we'll see that if these processing guarantees are held even in failure as well. And then we inject failures into our system. Failures can be categorized into three types: omission failures, or timing failures, or arbitrary failures. And these failures can be injected using any chaos engineering tools. Chaos engineering tools help us to inject infrastructure failure or network failures or application failures. However, in this study, we will focus only on infrastructure failure and network failures, as application failures can be minimized using TDD and proper unit testing. And then we will also inject this failure at the different part of the system, for example, at control nodes or the executor nodes. To measure the impact of a failure, we constantly monitor latency, throughput, and recovery time of the system after a failure. However, calculating the latency in a distributed system is not a trivial task, as there can be clock skew between different nodes, and the timestamp taken at one machine cannot be processed at any other machine. To counter this issue, we utilize end-to-end latency, where our driver inject the records in a multi-broker Kafka cluster, which are then ingested by our distributed stream processing system. And the output of this system is then ejected back into a multi-broker Kafka cluster, which is then read by the driver. And the time difference between the input and output is taken as the end-to-end latency of the system. Now let's discuss some related work. Karimov in his paper benchmarked Apache Flink, Apache Storm, and Apache Spark, and they explored the problems related to the measurement of a distributed system, and they defined latency and throughput terms, and they also separated the system on the test and the driver of the benchmarking tool. However, in their paper, they did not do any fault tolerance testing. In a paper titled "A Framework for Automatic Failure Recovery in ICT Systems by Deep Reinforcement Learning," authors proposed a reinforcement learning based recovery agent which can take appropriate recovery action in the case of performance degradation. However, their action space was quite limited as it can only restart the container. And also, their failure model was quite rudimentary as they focused only on node crashes. Now, I will conclude my presentation by summarizing my work in progress, and my planned future work. Currently, we are conducting an exhaustive study of impacts on performance by various faults in stream processing systems, where we have shortlisted multiple stream processing systems, and we are also injecting multiple types of failures, and we are also injecting these failure at multiple points in the system. And then we'll also see the impact of having different processing guarantees on the latency and throughput. After that, we will move toward our second research goal, which is to analyze the impact of the different configuration on a fault recovery performance. And then we will model the system in a reinforcement learning model and then develop the policy for the optimal recovery performance. With that, I conclude my presentation, and if you have any questions, please feel free to ask.